Hey everybody. So today we're going to talk about the mean value theorem. I like to think of the mean value theorem as a sort of Swiss Army knife in calculus. It is of great use for proving many important calculus theorems. The mean value theorem itself, however, tends not to be invoked very often in individual problems. At least that's my experience. A proof of the mean value theorem relies on deep properties of real numbers and the very nature of calculus. And so I think a proper rigorous proof is best left for perhaps a higher level math course, so we're not going to get into it in this video. However, the good news is the mean value theorem has great intuitive appeal. It's very easy to believe, and understanding the statement of the theorem really kind of helps clarify a lot of ideas in calculus. So let's look at the statement. Suppose f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So you might have a graph that looks something like this. Then, according to the mean value theorem, there exists some argument c strictly between a and b, and the value of the derivative at that argument is equal to the average rate of change of f over the whole interval. So graphically, this is really appealing because you could draw a segment whose slope is precisely the average rate of change of f on the interval from a to b. And because the function's differentiable everywhere between, it's smooth, so to speak. So you just can sense that no matter how you draw such a curve, there's got to be at least one place where the tangent slope is equal to the secant slope over the whole interval. And so here we have the location. We can sort of see where the location should be for f prime of c to equal this average rate of change. One thing to notice about the theorem is it just tells you that there exists some argument c. So there must be at least one, but there might be more than one. So it doesn't have to be a unique location where this happens. So here's an example where you can pretty well see that there have to be these two places at least where the tangent slope is equal to the secant slope over the whole interval. And the theorem also gives no general guidance as to the precise location. It just says there is some place. It doesn't really help you find it. So if you actually want to find such locations, you have to solve an equation. You have to set the derivative equal to the average rate of change on the whole interval and then try to solve that equation if you want the specific location of such an argument. So let's look at an example. Here's the function x squared. Now we know that x squared is differentiable on the whole real axis. So when we restrict to the interval from 0 to 2, it's certainly going to be continuous on the closed interval from 0 to 2, and it's going to be differentiable on the open interval from 0 to 2. And we can calculate the average rate of change over the interval 0 to 2, and it turns out to be 2. And we'll notice that the formula for the derivative function is 2x. And so we have this equation here. When is the tangent slope equal to the secant slope over the whole interval? And the mean value theorem asserts that this equation definitely should have at least one solution somewhere between 0 and 2. Now it turns out in this case, we can actually deal with this equation quite explicitly because we have the simple formula 2x for the derivative, and we have the value 2 for the average rate of change. It's very obvious that this has the solution x equals 1. But the thing to notice is 1 is in fact between 0 and 2. So in this case, there was only one such location between 0 and 2, and we could find it explicitly because we were able to solve this equation. Let's look at another example. This one's going to feel quite different. So here's a function. You should notice that it's just some combination of products and sums of functions that are differentiable on the whole real axis. So this function g that you create is also differentiable on the whole real axis, and therefore it's certainly continuous if we were to restrict to the closed interval from 0 to 2 pi, and of course differentiable on the open interval. So we have a function that's obeying the hypotheses of the mean value theorem. So what does that mean? Well, we could calculate the secant slope, the average rate of change from 0 to 2 pi. I invite you to do that. It's actually something that comes out quite nicely. You get 1. And then a good exercise is to apply the product rule and the chain rule as necessary. You find the derivative formula to be this huge mess. And now here's the general statement of the mean value theorem. Well, it's not the statement, but it's the equation that you should be able to solve. The mean value theorem asserts that this equation should have at least one solution between the argument 0 and 2 pi. Now when we substitute in the explicit data in this problem, we get this equation, which is rather eye-popping. So I just want to point out a couple things. One, I very seriously doubt most people would be able to look at that equation and say, oh, yes, it's quite obvious that there must be at least one solution to that equation between the argument 0 and 2 pi. That's not obvious at all, to me at least. But just given where this came from, we know that the mean value theorem asserts that it really must have at least one solution. And here's the other point. There's no way we're going to be able to solve this equation explicitly. It's just not doable. We're not going to be able to isolate x. So the theorem tells us there has to be a solution, and that's really sort of useful because we're not going to be able to find that solution explicitly. But that doesn't mean we cannot get our hands on these solutions, roughly at least. I mean, if you look at this picture, you can see that there really should be at least two places where the tangent slope is equal to the secant slope over the whole interval. And those two locations are very roughly 2 and 5, we can see in this picture. So let's get an assist from Desmos. You can plot the derivative. You can either enter the formula, or if you've defined g by a formula g of x in a previous line, you can actually just plot g prime of x. And you can plot the line y equals 1. And you can find the intersections. You can find the locations where the value of the derivative is equal to 1. And very roughly, to the nearest 0.001, those locations are 2.094 and 5.004. In any case, we see pretty good evidence that the mean value theorem was borne out, that there was at least one. In fact, there were two solutions to this equation on the interval from 0 to 2 pi. So now it's time for non-examples, or a discussion of what can go wrong when we relax the hypotheses of the theorem. So here's non-example A, and it's meant to illustrate that the continuity on the closed interval is required for the theorem to be valid. So we're going to define a function f, and we're going to define it to be 0 when x equals 0. We're going to define it to be the constant function 1 on the open interval from 0 to 2, and the value of this function will be 2 at the argument 2. Now, what does the derivative look like? Of course, the derivative is not defined at either endpoint, but it's certainly going to be 0 in between. So here's our derivative function. And we'll notice that the original function is differentiable on the open interval from 0 to 2, and it fails to be continuous on the closed interval. So it doesn't satisfy the hypotheses of the mean value theorem, and we're going to see that this opens up a loophole through which you violate the theorem. So if you calculate the average rate of change on the interval from 0 to 2 in this case, an easy calculation will show you that this rate of change is 1. But there is no argument in between 0 and 2 at which the value of the derivative is equal to 1. It's just not going to happen. All the tangent slopes are 0. So the mean value theorem fails. The problem is this function was not continuous on the closed interval, and that allowed a sort of loophole which made it possible for the theorem to fail. So let's move on to non-example B. And this non-example is meant to illustrate how the differentiability on the open interval is also required. So we'll define a function g this time. We'll define g of x to be x plus a half if x is between 0 and 1, and then we'll make a transition to the formula negative x plus 5 halves if x is between 1 and 2. So this function is not differentiable at either endpoint, of course, and it's not differentiable at 1 either. It has the same sort of problem that the absolute value function has at the origin. It's got a pointy place. So we notice then that the function fails to be differentiable on the open interval. It is, however, continuous on the closed interval. So now we calculate the average rate of change on the interval from 0 to 2, and that average rate of change turns out to be 0. Well, the instantaneous rate of change is either 1 or negative 1 throughout the interval, so there's no argument that solves the equation g prime of x equals 0. So once again, the mean value theorem fails. And the problem is, because the function is not differentiable on the open interval, This is the loophole through which the theorem can fail. Okay, so here's a potential application. To my knowledge, it isn't actually used anywhere in the world, but it could be. And so imagine you have a turnpike. It's a toll road, and you have sensors at each end to identify when a car goes in and out. And suppose the speed limit is 60 miles per hour throughout the turnpike. And now the turnpike is 160 miles long. And let's just say that you enter the turnpike at 7 and then you leave at 9. Now you could plot your position in miles as a function of time in hours, and your position function then would look something like this. Now, one thing to notice is we don't know anything about this position function in between the arguments 7 and 9. We will make some assumptions that seem to be consistent with our understanding of physics, namely that this position function should certainly be continuous on the closed interval from 7 to 9 and differentiable as well. And so if we make those modest assumptions, we would then be able to use the mean value theorem, because the average velocity on the interval from 7 to 9, easily calculated in this instance, would be 80 miles per hour. Now, that's above the speed limit for the turnpike, but you usually don't get ticketed for average velocities exceeding a certain speed limit. Usually, when someone gets pulled over for speeding, it's because pretty much their instantaneous velocity has been measured to be too high. In truth, I should add, it's not really an instantaneous velocity, it's an average velocity on a very tiny time interval, the kind of interval a radar gun is able to measure, but it's a good proxy for the instantaneous velocity. So usually when you get ticketed for exceeding the speed limit in terms of your instantaneous velocity. Here, though, we have this statement that your average velocity over the 2-hour journey was greater than the speed limit. But the mean value theorem asserts that there had to have been some time c when your instantaneous velocity actually was 80 miles per hour. So in theory, if you have sensors that are recording when you enter and when you leave a turnpike, and you might not even be speeding at those two moments, but if your average velocity exceeds the speed limit, then in theory you could be ticketed for having an instantaneous velocity somewhere along that 2-hour journey that exceeded the speed limit.